Greetings everyone, we are the HKU Unmanned Aerial Systems team. Today we'll be covering the technical design and flight readiness review for the SUAS competition. I'm Rico Zhang, and with me today are Tony, Andy, John, Sammy, Henry and Joshua.
We are HKU Unmanned Aerial System team from the University of Hong Kong. We are also an affiliated student interest group in 10 Wing Fan in the Wing. We have a team of 10 students in the development team. They are studying mechanical engineering and computer science. Our competition team consists of 6 people, with 3 operators. The operators include safety pilot, airdrop operator, and GCS operator.
We'll first go over the technical design of our UAS and then move on to its flight readiness. Let's first take a look at the requirements of this year's competition. This year's competition demands our drone to fly a sequence of waypoints autonomously with a maximum error of 25 feet. Then it's going to detect and classify a couple of standard objects in the form of alphanumerical specifically shaped signs and a single emergent object, which is a mannequin. Finally, we'll have to drop 5 objects to 5 separate locations, and these locations depend on the locations of the standard objects. Additionally, the drone must be able to fly for 12 miles, fully loaded, in one go. It's also going to be less than 55 pounds fully laden and be able to return home automatically if we lose contact with it for 30 seconds. As you can probably make out, the differences between SUAS 2022 and 2023 are substantial. Here we've got a diagram that describes these changes. As we can see, the payload carried is completely different. It's been changed from a UGV to 5 water bottles, and we no longer have to map an area using our camera. However, we need the ODCL system to communicate with the airdrop, which poses another challenge in itself. Over the course of the last 9 months, we've developed our UAS to hit all of these objectives. So let's have a quick look at our design. Our drone is a quad rotor, basically a 50 by 50 inch square and around 20 inches tall. It's around 15.5 pounds in weight and flies at a top speed of 31 miles an hour. As it's a quad rotor, it can turn on a dime, therefore it's got a minimum turning radius of 0. From the photo we can see that it's got a sturdy landing gear and plenty of space underneath it for carrying 5 16.9 ounce water bottles. It's controlled by the Pixhawk 4, allowing it to fly automatically over the 2.4 GHz wavelength.
The camera of the drone was chosen after comparing possible candidates based on these 6 criteria, especially the ground sampling distance. After comparison, GoPro Hero 11 Black action camera was chosen because of high resolution, smaller weight, and its built-in stabilization. The most significant feature is its low ground sampling distance, which means more data and details can be included in a single pixel. The video capture, Speedy FPV 2-axis brushless motor camera gimbal was used as it is highly compatible with the GoPro camera and has low weight. For computer, Jetson Nano was chosen and attached to the UAV because of its low weight and sufficient computing ability for the ODCL mission. The aerial image taken with the design imaging system. Detection, classification, and localization. Standard object detection consists of 4 stages with 3 types of algorithm used in total. First, in the aerial image, the region of interest with the standard object is detected using YOLO. The region will be cropped according to its boundary box and passed to the second stage. In the second stage, the state of the object is classified using YOLO. In the third stage, based on the cropped image from the first stage, the alphanumeric on the object is classified using YOLO. For the last stage, K-means clustering and OpenCV are used on the cropped image to extract the 2 colors of the object and the alphanumeric on it. For ODCL is trained by creating the dataset with the use of RoboFlow site. Our team created a program script that can create a number of aerial images with the standard object artificially. Around 10,000 of artificial aerial images were used in each stage and went through image augmentation.
Hi, my name is Sammy Wong and I'll be responsible for the airdrop system in the technical design review. We designed a dropping platform to accommodate the imaging system above the platform and also the airdrop system below the platform. It is mounted below the quadcopter airframe with features such as detachable design and reserved space for gimbal and landing gear. Same as most of the airframe, it is made from carbon fiber. For our dropping method, we decided to use controlled free-falling method by using a parachute. The payload of the drone will be 2 water bottles, each attached with a parachute through duct tapes. In order to deliver all 5 water bottles, we'll fly the drone 3 times, with the first 2 times carrying 2 water bottles and the last time carrying only 1. We decide the size of the parachute by using the drag equation and targeted the terminal falling speed at 3.5 meters per second. For reference, human falling speed is around 5 to 6 meters per second with a parachute. Therefore, the targeted speed is safe for payload dropping. The calculated parachute size has a radius of around half meter. For the dropping mechanism, the water bottles are secured horizontally under the dropping platform with thick heavy-duty rubber band. When the servo motor rotates, it will release the payload and it will fall with the parachute, which opens mid-air. For optimal dropping time, since we are using multi-copter drone with hovering capability, the servo motor can be activated and drop the payload once it is above the target.
And this is about the communication distance test, and the figure can show that the signal test result on the open area for the devices that the bandwidth of connection is 65.5 Mbps for a 200 meters distance, which is show this stability and constants of the device. And the next figure also can show the connection is 74 Mbps for around 200 meters, which is so the actual value is only 10% error with the familiar
My name is Lee Simpun Tony, and I will talk about the design of the aircraft. For the airframe, we selected the quadcopter because it can hover and have a high stability. Moreover, it can take off and land vertically, therefore it requires less space. And here shows our label diagram in our quadcopter. It consists of the GPS, the batteries, the flight controller, and a landing leg, and with a propulsion system which is 607X. To cover the battery, we have designed a 3D printed cover. For the manufacturing process, our major use of material is carbon fiber plates and carbon fiber tubes because they are light but strong. And here shows the carbon fiber plates manufactured by the water jet cutting. And the photos on the right shows the assembly of the UAV. And here's talk about the T-Motor 607X propulsion system used in our quadcopter. It consists of the brushless motor, the electronic speed controller, and the propeller. 607X is chosen because of its light weight. And the thrust to weight ratio of the quadcopter is 2.39, as the takeoff weight of the UAV is 9 kg. And we can conclude that the total thrust is larger than the weight, therefore it is able to take off and hover. Finally, here shows the specification of the quadcopter. The takeoff weight of the quadcopter is 9 kg, and we use the 2 Max-M 6 cells 11,000 mAh batteries in series. And here also shows the dimensions of the quadcopter.
Hello, I'm John, and I'm going to talk about autopilot. When it comes to our autopilot, we use Pixel 4 Mini. It has some features like built-in inertia measurement unit and barometers to help keep UAV stable in flight, and we have got an external GPS to help it navigate. We have got a Jetson Nano on board for object detection and classification. For ground control station, we use Q-Ground Control. It allows for easy UAV configuration and setup of flight boundaries, as well as the ability to set up and monitor flight plans, and features such as real-time monitoring of UAV speed and altitude. In case of any unexpected situations, it also has a fail-safe system to return home or land directly.
So here's the alternative considered for the UAV. So here's the first alternative. This is a helicopter. It provides a larger weight capacity. Each propeller size can be smaller and longer flight time compared to the quadcopter. But the alternative didn't meet the acceptance criteria, and the alternative was more costly, so it was not chosen. So here's the second alternative, the fixed-wing aircraft. So it provides a higher endurance and compared to the multi-rotor, and it flies faster and the less thrust is required. But it needs extensive analysis on the airflow and it cannot hover, so it was not chosen. So it is the final alternative. It is a hybrid aircraft, so also known as the vertical takeoff and landing aircraft. So it can hover and reduce the thrust during the cruise, but it is a more complicated system, and the hover and the cruise transition may not be stable, so it is also not chosen.
In this part, I'm going to talk about safety, risks, and mitigations. For development process, we have done indoor tests with safety barrier to make sure our propulsion system can meet performance requirements. We also take measures to protect our electrical components by enclosing them in 3D print casing. And to make sure our safety pilot is well prepared, he practiced in flight simulators and got practical experience with small drones. During mission, we have implemented a fail-safe system that will bring our drone back home or land it safely in case of equipment failure. We are also careful to check the weather before each test flight to make sure conditions are safe for flight. And to prevent any human error, we always use a pre-flight checklist to double-check that all of our components are assembled and calibrated properly.
The initial system was tested on using the real area image taken with our drone. In the first stage, objects can be detected with more than 80% precision. Second stage, shapes can be classified with more than 95% precision. Third stage, itinerary can be classified with more than 95% precision. Last stage, color classification is done by using K-means clustering and OpenCV. Colors of the object and the letter can be classified well. Emergent objects, by using YOLO and a similar method, they can be detected with more than 75% precision. Also tested with the real aerial image showing more than 75% confidence score. Digitally transmitted to the ground station using Ubiquiti device.
Now I will talk about the airdrop performance in the flight readiness review. For our airdrop performance test, 12 tests were performed. They are tested only above high building for legal and safety reasons. The altitude is around 25 meters. There were total 10 successful tests, with one test failing because of servomotor malfunction and unable to rotate. And the other unsuccessful trial was due to being out of target distance. The 90th percentile distance from target is roughly within around 3 meters. The next slides will show one of the successful tests. The parachute opens mid-air not too close to the mechanism, which prevents it from being stuck at the drone wall mechanism. It also ensures the landing to be accurate and close enough to the target. At the same time, the parachute did open high enough above the ground for deceleration. Therefore, the parachute and the drop mechanism is successful overall.
This part is about the communication distance test, and the first figure actually is show the signal test result on the open air for the device, and the connection is 65.5 Mbps for a 200 meters distance, which is show the disability and constants for the device connection. And the next one is the view result, which is can see the that one is the familiar result, which is 74 Mbps for 200 meters, which is only 10% error with the actual value with the signal in our real life.
In these sections, I will talk about the flight readiness review of the aircraft. 40 flight tests were conducted, including the manual and autonomous control, and the total flight time of the quadcopter is around 2.5 hours. Here shows the flight performance of the quadcopter. The flight wing is 12.2 miles and the hover flight time is 28 minutes. The turn radius is nearly 0 meter, as you can see the quadcopter can turn at the waypoint. Moreover, the angle of climb and angle of descent is 90 degrees because the quadcopter can take off and land vertically. The maximum flight altitude tested is 25 meters, and the takeoff and landing area can be as small as 3 meters by 3 meters. Therefore, the quadcopter can fulfill all the minimum required performance in the competitions.
Now I'm going to talk about autopilot in flight readiness review. Our UAV is performing really well. It can perform autonomous takeoff and landing, and it is super accurate when it comes to hitting waypoints. Additionally, we can control its velocity and altitude with precision. Our drone's flight performance is impressive. In the last 5 autonomous flights, we hit all 100 waypoints with an acceptable radius of 5 feet and didn't miss any of them. So our average waypoint missing error is 0. We also spent 3 minutes in manual mode per flight for manual takeover and landing.
So here is the mission testing session. So here is the autonomous flight test. So as you can see, here is the taking off point, dropping point, and the landing point. Here is the flight log diagram for the autonomous flight test. So as you can see, the UAV almost follows most of the path in the flight test, so which is show the high performance in the autonomous flight. Here is the other mission test of the UAV. So the airdrop test. So since the airdrop test cannot conduct in the Hong Kong, so there is no result for the airdrop test. For the ODCL test, the precision rate close to 99%, so it is believed that it has the high accuracy for the object detection. So as you can see, the test result shows the high performance in the mission and it satisfies the competition requirement. So it is believed that we're ready for the SUAS 2023.
So in this last section, we're going to talk about how our UAV is going to meet all the flight performance requirements. So in this video, we can see that the UAV is able to manually take off, fly 1,000 feet away from the pilot, and then land. And in this video, we can see that the UAV is able to autonomously take off, fly 200 feet away from the pilot, transition to manual mode, and then land. Our quadcopter is also able to fly 12 miles fully loaded, all above 75 feet. It can also reach all the waypoints with a max error of much less than 25 feet. And we have also exploited the advantages of the quad-rotor design, that being having a non-existent turning radius, and also a freely adjustable angle of climb.
That's the end of our technical design and flight readiness review video. Thank you.